on December 5th, 2022, the Lawrence Livermore National Laboratory in California did the impossible. For the first time in human history, using fusion energy, they produced more energy than they put in. A lot of experts thought that this would be impossible for the foreseeable future, but while this achievement is ample cause for celebration, all is not as it seems. Since its devastating use in the atomic bomb in the 1940s, it didn't take long for scientists to figure out something very clever. Instead of splitting atoms apart to create energy, called a fission reaction, in theory, it would be possible to fuse the atoms together to create energy. And this is called a fusion reaction. If done correctly, it could be a very useful source of generating clean power. Useful is actually an understatement. In fact, unlike traditional nuclear bombs, hydrogen or otherwise, that contain at least some part fission reactions, or nuclear power stations that also split atoms apart, a fusion reactor would produce no long-term radiation or radioactive waste. In fact, the main byproduct is helium and some neutrons. Further to this, there's very little environmental impact, and the fuel is abundant. In essence, wherever there's water, there's fuel for a fusion reactor. Well, this isn't entirely true, and it could actually be a big problem, but another positive is that meltdowns are impossible. This is because it actually requires energy to keep a fusion reaction going. If there's any kind of problem, the reaction stops in a matter of seconds because there's no energy to keep the reaction going. And lastly, and best of all, fusing atoms together creates 4 million times more unit energy than burning coal or gas, and 4 times as much energy as the more dangerous nuclear fission used in traditional power stations, that is, splitting atoms apart. So you might be wondering, doesn't nuclear energy lead to radioactive disasters? Don't atomic bombs use nuclear energy? Well, it turns out atoms like to stay together, and they don't like to be broken apart. So when you do this, there's a great deal of harmful radiation. But when you fuse atoms together, it's not so much the case. And for those who know a bit more about atomic tech, you'd be thinking about hydrogen bombs. Well, yes, fusion is a part of it, but the fusion part is only there to aid the fission part. The fusion part involves uranium, which is still a very dangerous material. Funnily enough, fusion is completely natural. For proof of it, just look up at the sky during the daytime. It's called the sun. It's a giant fusion reactor in the sky. If we could do this on Earth and control the energy released, it would be the biggest change to the course of human history. The feat is almost impossible, but the benefit is so great that it's worth a shot. A lot of scientists thought so too. So scientists around the world have been getting to work to make it happen. So how does fusion work exactly? Well, bear with me on this next part, because the understanding of this is crucial to the understanding of the rest of the episode. Under ordinary circumstances, atomic nuclei carry a positive electrical charge. This positive charge repels the nuclei so they don't get too close to each other. Frankly, they hate being next to each other like two friends who have fallen out. But when heated to temperatures of millions of degrees, the electrons say sayonara and leave. The nuclei are now vibrating around like crazy in a superheated soup called plasma. In this plasma state, the positively charged nuclei can get enough speed and energy to overcome their mutual dislike for each other. And when they get close enough, a new short-range force takes over, called the strong nuclear force. And when this takes hold, the nuclei combine and fuse. And when this fusion happens, energy is released. And the cool thing is, you don't need a lot of matter to create a lot of energy. You probably all know E equals mc squared. It's a very powerful equation. Just to give you an idea, converting 700 milligrams of mass into pure energy is equivalent to the energy of the bomb dropped on Hiroshima. Elements such as hydrogen and helium are used because these atoms require less energy to overcome their natural repulsion to each other. And just as a side note, the Sun and other stars can overcome the repulsion of atomic nuclei intrinsically due to the immense gravity generated because of their huge mass. Essentially, the gravity just squishes the atoms together so fusion can occur. So back here on Earth, how exactly do you beat nature and fuse these atoms together? Well, in order to get atoms to overcome their opposition to each other, you have to get them moving really, really fast, and in a confined space. The goal is to create a high energy state of matter. There are two main ways to do this, but the one we'll focus on for now is called internal confinement fusion, or ICF. This is where a tiny capsule containing hydrogen fuel is blasted with lasers for less than a billionth of a second. But why for such a short period? Well, if these lasers were fired for any longer period of time, the energy from the lasers would spread out over a larger area, and the pressure and temperature inside the fuel target wouldn't be high enough to cause the atoms to fuse. After blipping the lasers, the hydrogen fuel heats up and expands, resulting in a reflective shock wave that compresses it. The density becomes so high and the nuclei are so close to each other that the probability of collision is high. Under these conditions, some of the nuclei fuse, and some of their mass is directly converted into energy in accordance to E equals mc squared as discussed earlier. Okay, so that's all well and good, but how come this is taking so long? Over the course of decades, it has been very slow going for atomic fusion energy. As the publication Vox so eloquently put it, fusion reactors so far are like using a blowtorch to light a match. Sure, it works, but the energy that you've put in to light that match was excessive for the small flame of energy that you get out. As time wore on, there was little to show for fusion, and the investment into fusion energy never grew and progress started to slow. In 1997, the United States Department of Energy decided to throw their weight fully behind fusion energy. You see, the National Academy of Sciences, a private organization but official advisor to the US government, stated that one of America's goals should be viable fusion energy. To be viable, ignition needs to be achieved. This simply means more energy out of the fuel target than the amount of energy hitting the fuel target. To achieve this goal, the National Ignition Facility was built. Construction started in 1997 and concluded in 2009. When experiments started, things didn't go so well. By 2012, they had only achieved 10% of the conditions needed for ignition. After this, the facility was then converted and partially used for, you guessed it, weapons research. You see, this was very disappointing for the Americans because even as far back as 1997, the Europeans had already achieved 67% of ignition conditions. They were using a more widely accepted and thought to be more feasible method, and we'll get to this later in the episode. But the Americans persisted, and they started to get closer and closer and closer. In 2021, they ended up getting 70% of the way there, but in late 2022, they made some improvements to the fuel target design, and in one fell swoop, achieving 154% of ignition conditions, they got more energy out of the reaction than they put in. On December 5th, 2022, the American team turned on one of the most powerful lasers in the world. They stood by as 192 laser beams smashed into a tiny fuel pellet. 2 megajoules of energy went into the laser beams, and 3 megajoules came out. America had beaten the Europeans to this moment, and Energy Secretary Jennifer Granholm could relish in this fact. Quote, "This is what it looks like for America to take the lead, and we're just getting started." In the scientific community, the reaction around the world was ecstatic. Carolyn Kurantz, a plasma physicist at the University of Michigan, states, quote, "The result clearly surpasses that mark, leaving no question that they have achieved fusion ignition in the laboratory." But before everyone celebrates, there's still a lot of work to be done to make fusion a viable source of abundant clean energy. There's a vast amount of engineering optimization needed here. Let's see what that is exactly. Amazing as it is, so far the breakthrough just isn't practical. The National Ignition Facility itself is just a research laboratory first and foremost. They're essentially testing the feasibility of the theory. The technology is not intended to produce power, so designing an actual whole fusion reactor to harness this new approach will be in its own right a massive engineering challenge. In news publications, it's widely stated that the lab produced 1.5 times as much energy than was used to cause the reaction by the lasers. But there's a massive catch. This measurement only accounts for the energy in a very narrow way. It only considers the actual laser energy hitting the fuel target. If this method is to be feasible for the energy grid, you have to account for the energy needed to power the lasers themselves. Taking that into account, the total amount of energy output would need to be roughly 66 times more than was produced. Another limitation is that the facility can only fire a few laser shots per day, and the amount of electricity needed can sometimes cause blackouts in the lab. To run an actual fusion reactor, you'd need about 10 shots per second. Another massive issue is what I touched on earlier about the fuel source. The fuel source for fusion reactors are two isotopes of hydrogen, deuterium and tritium. Now, deuterium is plentiful. About 1 in every 5,000 hydrogen atoms in the ocean are deuterium, and it sells for about $13 per gram. But tritium, on the other hand, is extremely rare. To produce the material costs about $30,000 per gram, so this is a major issue. But on the bright side, fusion reactors themselves do produce tritium as a byproduct, so ultimately it would have to be a matter of capturing it effectively. Right now in the world, there's only a few kilograms of commercially available tritium, but the hope is, in the far future, as fusion reactors come online, we'll be able to obtain more of that material. Though getting adequate fuel is going to be a really hard problem to solve, but there are some much easier problems to look at first. Namely, the combustion of the hydrogen fuel itself. It's not burning that effectively. Troy Carter, a plasma physicist at the University of California, explains, quote, "The National Ignition Facility shot only burned a small fraction of the fuel in the capsule. If you can find a way to burn up more fuel, the gain goes up substantially." This will of course involve more tweaking to get all that laser energy directed towards compressing those hydrogen atoms. Interestingly, the biggest gains could be made from the lasers themselves. The National Ignition Facility is using outdated technology. The lasers are only 1% efficient in terms of turning electricity into laser light, while modern designs can be 20% efficient. Kim Boodle, director of the Lawrence Livermore National Laboratory, said this, quote, "The National Ignition Facility is built on 1980s laser technology. So even with the same setup, just by using better lasers and targeting the fuel more efficiently, there could be plenty more energy output to gain. I kind of see this whole situation as equivalent to the first transistor versus a fully working silicon chip of the early 1980s. We have the concept, but in order to make it practical, there still has to be orders of magnitude of engineering breakthroughs needed." So the National Ignition Facility may have proven that their method is viable, but is it the best way forward or a dead end? Well, it's hard to say, but this is where the other approaches of nuclear fusion come into play. In the race for fusion energy, there are two main methods. The internal confinement method using lasers, which is what I've talked about so far, but there's another version that uses magnets. It's called magnetic confinement fusion. The most common way to achieve this is by using electromagnets, microwaves, and particle beams to heat hydrogen gas and turn it into plasma. This plasma gets squeezed by superconducting magnets in a donut-shaped ring. When the plasma is hot enough and the atoms are close enough together, fusion can occur, and a large amount of energy is released. And this method is the widely accepted method, and until December of 2022, it was the method that was generally thought to lead to ignition. This magnetic form of fusion is how the ITER, the world's largest fusion project currently under construction in southern France, will generate the reaction. After fusion occurs, heat from the reaction can be used to warm water, heated up to become steam, and this steam can drive a turbine to produce energy. This last part is basically how every form of major grid energy is produced, from coal to nuclear. The energy is simply used to heat up steam to drive turbines. Thinking about it, it sounds a little inefficient, but there may be a better way. More recently, there's been a third method, a nuclear fusion generator called pulsed compression. This method doesn't heat up steam, but can provide electrical energy directly. So in conclusion, while fusion energy is largely still a dream, it's come one large step closer to reality thanks to the National Ignition Facility. But there's still likely decades of work ahead of us. But who knows, there could be a technological breakthrough in materials science, new methods, or other facets of technology, and we could see a breakthrough sooner than we think. I'm personally interested to see what independent groups come up with, those like Helion using their pulsed compression technique. If scientists are willing to share their knowledge and collaborate, and maybe even future AI systems could help with this, fusion energy may no longer be a pipe dream.